Hey guys, welcome back once again. We already know to turn on an N-channel MOSFET, we need to charge the input capacitor by at least providing the gate to source threshold voltage of the MOSFET. This is the basic requirement. Well, it's not that simple. In this video, we'll see why a MOSFET needs a gate driver circuit. So let's start. We can provide a basic gate to source threshold voltage through any logical circuit like this to turn on the MOSFET, which are very easy to drive small current loads like 12-volt relays, small LEDs, and resistive loads. But sometimes just 5 volts is not sufficient to turn on the big power MOSFETs. If the load is very powerful and conducts very high current, in that case we need to provide gate to source voltage sufficiently higher than the threshold voltage to turn on the MOSFET fully. As we have already seen in our last video, there is an inverse relationship between RDS on of the MOSFET and gate voltage. So in that case, we need to provide the voltage conversion circuit to turn on the MOSFET, where if you provide 5 volts, then the MOSFET gate should be sourced by 15 volts, which certainly looks like this. This Q2 is our power MOSFET. Q1 is logic MOSFET which switches our main power MOSFET. The gate voltage of the power MOSFET is driven by the VDD, which is 15 volts. When the high pulse to turn on the power MOSFET is provided to this NOT gate, this logic circuit gives low pulse to this MOSFET Q1 and it turns off. When the MOSFET Q1 is off, the current flows to the resistor R2 to R3 and it turns on our main power MOSFET. When the low pulse is provided, this NOT gate gives high pulse to the MOSFET Q1. This Q1 turns on and pulls down the VDD to logic level low. As there is no gate voltage to the power MOSFET, the MOSFET turns off. This is how a small logic pulse of 5 volts or 1 volt can turn on a power MOSFET with gate voltage of 15 volts. Well, this type of circuit is very simple and useful, but these options slow down the switching speed of the MOSFET and therefore increases the switching loss. On the contrary side, reducing this R2 causes a large drain current to flow through the MOSFET Q1 during the turn-off period of the power MOSFET Q2, which increases the power consumption of the driver circuit. Also, it is very important that we should not exceed the gate to source maximum voltage rating as well. If we do that, it will cause the destruction of the MOSFET. But even if we keep the gate to source voltage below the maximum rated voltage, the stray inductance of the gate connection present in the circuit gets coupled with gate capacitance of the MOSFET. Due to this, the coupling voltage ringing occurs, which could lead to the destruction of the oxide layer of the MOSFET. To minimize this problem, we can drive a MOSFET through a gate driver IC or proper gate driver circuitry. A gate drive circuit has a very low output impedance. Because of that, the gate voltage doesn't exceed the maximum gate voltage during the normal operation, and it doesn't cause any voltage ringing in the circuit. When we use the driver circuitry to turn on the power MOSFET, a certain charge has to be supplied to the gate to raise it to the desired voltage level. The large power MOSFET has higher gate capacitance. So, the gate driver acts as a voltage source capable of supplying the right amount of current in the shortest possible time, which charges the input capacitor. Also, while turning off the MOSFET, this input capacitor should be discharged as soon as possible. So this MOSFET gate driver gives the low resistance part to discharge this capacitor. This is how a basic MOSFET gate driver helps to switch the MOSFET. The MOSFET gate driver provides important features such as low voltage compatibility. We can provide a voltage pulse at the input of the MOSFET gate driver as low as 1.2 volts, which minimizes the power losses at the input. And still the gate driver gives high gate voltage to turn on the MOSFET. Second is the transient protection. The switching of the MOSFET sometimes causes the back current from the gate to the MOSFET driving circuitry due to the transient occurred in the drain of the MOSFET. This transient might flow from the gate to drain capacitor of the MOSFET and damage the main logic driving, which is the actual brain behind the system. But these MOSFET drivers are tolerant to negative transients and protect the logic devices from such transients. Third is the switching speed. The MOSFET gate drivers are very useful for fast switching applications and minimizes the switching losses of the MOSFET. MOSFET turns on and turns off with high switching speed in many circuits such as switch mode power supplies and motor controllers. Fourth is the isolation. Many MOSFET gate drivers provide optical or galvanic isolation between main logic circuit and high power circuit. Well, this is just for the low side drivers where the MOSFETs are used as low side switches. It is very hard to turn on an N-channel MOSFET if it is used as a high side switch. And this is where a high side MOSFET drivers also come into picture, which are easily controlled by a small logic pulse voltages. I hope you understand why we actually need a MOSFET gate driver. Next time, we'll see what's inside and different types of MOSFET driver circuitries. Till then, stay tuned. I've added all the reference on this topic in the description. I hope you got something from this. If you haven't, you can watch the video again. Still, if you don't, you can ask your doubts in the comment box below. Hit the like button if you like this video, subscribe to my channel, and finally, thanks for watching.